So at the end of last class, we finished with defining the so-called green strain, Lagrangian strain. So that's 1/2 FTF minus I, right? So just to point something out, if you remember, we had that the deformation gradient F, right, is grad U transpose plus I, right? And where this gradient operator is with respect to big X, right, in the reference configuration. So let's plug this in back into that guide, keeping in mind that we have to have F transpose. Well, that's just grad U plus I, right? And that's the transpose of the addition. And the transpose of the identity matrix is the identity matrix. Right? So if we plug that into back into this equation to get everything in terms of grad U's, then we'll have that. Or if we write this in additional notation, where, keep in mind when we have a repeated indice, K in this case, it's a summation, okay? So if we were to linearize this, remember this green strain is a fully geometrically nonlinear measure of strain, okay? And it again refers back to the reference configuration as the normalization. So if we were to linearize this, or ignore higher order terms, then we get something called the linear strain. We typically use a little epsilon for that. And it's just grad U plus grad U transpose, or okay, so this is the linear strain, sometimes also known as the Cauchy strain. Now, how many of you have seen that before? This definition of strain. If you've ever had a class in elasticity, right, that's the definition of strain. But what I'm showing you here is that it's not, in fact. It's the linear definition of strain, or the linearized strain. And so if you have large deformations, this strain measure is invalid. So what's a large deformation? Well, typically we use the rule of thumb that the gradient of U must be, the magnitude of the gradient of U must be much, much less than 1. Where the magnitude, remember, gradient of U is a tensor, so the magnitude operation would be something like the square root, or let's just say the magnitude of a tensor A is the square root of Aij, Aij. So that's also known as the double contraction, right? So there's two summations there, 1 over I, 1 over j. And so this results in just a number, a single number, right? I mean, how else can I compare something to 1? It has to be a number, a scalar. So this is a double contraction. It gives you a scalar. And so that's the rule of thumb we use for what a large deformation could be. And you notice I'm saying a lot of times this theory that I'm showing you is called finite strain or large strain. But notice our definition is not based on strain. It's based on displacements, right? U is displacement, okay? I think I was misspeaking. I was calling the gradient of U the deformation gradient. It's the displacement gradient, right? So our definition for what a finite, or when we need this large strain or finite strain theory is based on the displacements. And the reason for that, and we'll see more later, if you imagine a very, very kind of long, slender member, and this is just an example, right? But imagine a very, very long, slender beam. If I hold this side fixed and I apply a force to that side and I get some deformed configuration, I can have very, very large deformations without very much strain. So if you were to compute the actual strain in the bar in this little long, slender beam, the strain can be really small, but the deformation is clearly very large. And so in these situations, it's, deformation is strain plus rotation. And so in the cases where you have even small strains but finite or large rotations, you really have to use this fully nonlinear theory, right? And so later in the class, really this is, I'm presenting the fully nonlinear theory, but later when it's convenient or under the assumptions that seem reasonable, namely in a geomechanic or a reservoir setting, we don't have large rotations typically, right? And our representative volumes are large enough, maybe the size of this room in some cases, that the small strain theory holds. But you really need to be aware of the limitations or the restrictions of this theory, okay? And so, yeah.
So do you mean the conscious strain is used for the large deformation, but with the small displacement gradient?
This is my definition of a small displacement gradient. And when this holds, the small strain theory is a good approximation, okay? When this doesn't hold, right, if you were to compute this and it's on the order of 1, you really need to use a finite strain theory. And I'll have some more examples in a second to show you why, and then also your homework will, you'll work some problems that show that a very large difference in the but, so the point is just to show you that everything, unless anyone's taken a course in continuum mechanics and have seen the green strain before, your whole worldview of strain is this thing, right? And I'm telling you it's wrong. Or it's an approximation to the real strain. This is the real strain. Or it's a measure of the true geometrically nonlinear strain.
Maybe there's a miscommunication. I think the question might specifically be, in the case of small strain and finite rotation, which strain measure do we use? Do we use the fully nonlinear measure?
The fully nonlinear, yes. Yeah. So if you have this scenario where you have small strain but large rotation, you have to use the fully nonlinear theory. Right? And so, two problems that come to mind immediately in a petroleum engineering or reservoir setting is sand production. In sand production, you have very, very large deformations and rotations that lead to basically material separation, that lead to sand production. And the other thing is if you're actually working with casings in extended reach horizontal wells, there you have very large rotations, right, in the casings, but small strains.